In this video, I'm going to be talking to you about radical expressions. So let's go ahead and get started. It says, let's see, we're only going to be using real numbers here, so keep that in mind. On 1a, we need to find the square root of 121. So that means we need to figure out what number do we square to get 121. So when you're doing these problems, it's going to be important that you know your perfect squares. So I'm going to go ahead and write those down, and in this case 11 squared is 121, so that's my answer. But here's our perfect squares, and these are the ones that you ought to know, the ones that we run into the most. You should know up to 12 squared or 144. So 1, 4, 9, 16, and so on. These are what we call squares or perfect squares. And when we're taking the square root of a number, these are numbers we want to recognize. So on letter B, the square root of 64 we know is 8. And we're going to be, we can put a little 1 out in front there. It's really negative 1 times the square root of 64. That's what this expression means. And so we get negative 8. So notice you take the square root of 64 first, and then multiply by negative 1. Now on letter C, notice we're looking for a number that you square and you get negative 64. Well, any number times itself is always going to be positive if it's a real number. So this can't happen with real numbers, so we would say not a real number. Now when we extend our numbers to what we call the complex numbers, we'll be able to handle this problem a little differently. Let's look at letter D. So now we're looking to find the cube root of a number, 125. So we're looking for some number that you cube to get 125. So here's our perfect cubes. So notice 125 is 5 cubed, and so the number that you cube to get 125 is 5. So you got to know your perfect cubes when you're doing cube roots. And for fourth roots, we want to look at our fourth powers. So these are the ones we see the most often, and so we're looking for a number that you take to the fourth power to get 16, and of course that would be 2. On number 2 here, it says in the expression the cube root of 5, the 5 is referred to as the, well, it's under the radical, so we call it the radicand, and the 3 is referred to as, it's what we call the root or the index. I'll normally use the word root because when we say that expression we use the word root, but either word can be used. On number 3, turns out there's a relationship between radicals and roots. I'm sorry, radicals and fractions as exponents. And also we want to talk or look at what we can and can't do when we work with radicals, or how we multiply, how we add them, that kind of thing. So on 3a, first of all, that one is true. It turns out that your base becomes your radicand, and the denominator of the fraction becomes your root. Part B, or letter B, is false. Notice the denominator here is n. That should be my root. So this one is just flipped. It should be the nth root of a to the n power. Now we can actually put the m on the outside of the whole radical, and sometimes it's better to put a radical in this form. And you'll see that in a little bit here. On letter C, that is true. That is how we multiply radicals. So the square root of 3 times the square root of 5 would equal the square root of 15. You can actually write these both as, well, a to the 1/2 power times b to the 1/2 power, and you can use a rule of exponents to show that these two expressions are equal. So basically the foundational rules for exponents are what justify what we're doing when we multiply radicals. Now on letter D, this actually turns out to be false. So if you were adding the square root of 3 plus the square root of 5, you would find that it isn't equal to the square root of 8. You could actually use a calculator to show that this is the case. Unfortunately, it doesn't work this way, although it'd be nice if it did. So it works with multiplication this way, but not with addition. All right, next it says two radicals can be multiplied together if they have the same root, and that is correct. So if we have the cube root of 2 times the cube root of 5, we get the cube root of 10. So this works not only with square roots, but with other roots as well. As long as the roots are the same, you can multiply the radicands. Again, this goes back to some rules of exponents, or to a rule of exponents. Let's look at F. It says a square root expression is not simplified if its radicand has a perfect square factor other than 1. And this is true. So for example, the square root of 15 is considered simplified because if you look at our perfect squares other than 1, and in fact 4, 9, and 16, that's going to be enough here to see 15 is not divisible by any of these numbers, certainly nothing bigger, and so this is simplified. Whereas if we had something like the square root of 12, notice 4 is a factor, and so this is not considered simplified. So in just a few minutes we'll actually practice simplifying radicals, but before we do that, I want to make sure you can go back and forth between radical form and fractions as exponents. On 4a we have the fourth root of x, which would be written as x to the 1/4 power if we're using rational exponents, fractions as exponents. Now on part b here, square root of 10, there's actually an understood 2 here, so this is 10 to the 1/2. So anytime you have a square root, you could write that as the radicand to the 1/2 power. On letter C, you would get x to the 2/5. Remember that the denominator should be the root. Now be careful on this one. Your base is everything that's inside the radical, or your radicand, so that'll be to the 1/3 power. Now you may wonder, do I really need the parentheses there? And the answer is yes. If you wrote it as 5 times m to the 1/3 power, the 1/3 actually just goes with the m, and so this would be 5 times the cube root of m. So it's not the same. You got to have the parentheses. Let's look at number 5. You have x to the 1/2 power. We know anything to the 1/2 power is a square root. Again, I could write the 2 as my root, but we don't normally write that. It's understood to be a 2. A to the 3/4 power becomes the fourth root of a cubed. And we also know that we can put that exponent on the outside. So either of these is correct. Letter C, this is the square root of 49. Our directions are to simplify if possible, and that would be 7. On letter D, we have the cube root of 8, which we can simplify. Let's see, we need a number that you cube to get 8, and that would be 2. All right, on letter E, let's see, 64 is going to be our radicand. Our root is 3. Now at this point, I could put the 2 right here, but I really don't want to square 64. That's a pretty big number, and then have to take the cube root of that. So I'm not going to do that. I'm going to put this in the other form. So notice inside the parentheses is the cube root of 64. So I'm looking for a number that I cube to get 64. That would be 4. And then don't forget the 2 from the outside, my exponent. We're going to get 4 squared, which is 16. All right. On number 6 here, now we're simplifying. So let me write down our perfect square factors other than 1. So certainly 4 is a factor of 20. So we can actually break this down into the square root of 4 times the square root of 5. So I'm always going to put my square root that's a perfect square first, and then what I call the leftover factor, in this case the 5, in my other root. And so now I can simplify this because the square root of 4 is 2. And so the simplified form of the square root of 20 is 2 square roots of 5, or 2 times the square root of 5. If you look at letter B, notice that 9 is a factor. So again, I'll put the 9 first. Square root of 9 we know is 3, and so we get 3 square roots of 6. On letter C, we can factor out of 4. So here we get 2 square roots of 11. On letter D here, you got to be careful. You might try using 4 and 12, and you'd get 2 square roots of 12. But the problem here is, look at the 12. It still has a perfect square factor of 4. So what that tells me is there's a bigger perfect square factor. And so I'm going to start over. Normally it's easiest just to find the biggest perfect square factor. Let's see, 9 is not going to be it. 16. That's what we need. Notice 16 times 3, and 3 has no perfect square factors. So 4 square roots of 3 is my answer on this one. Now, we talked earlier about how we can't take the square root of a negative number. However, that being said, there was a time when mathematicians were solving all sorts of equations, and they were constantly having to throw out possible answers because of situations where they had the square root of a negative. So finally someone said, hey, I think this is ridiculous. Let's call I the number that you square that gives you -1. So I is equal to the square root of -1. These two expressions are equivalent. So I is the number that you square to get -1. So if we do that, I can actually rewrite each of these problems. If I have a square root of a negative, the first step is just to put a square root of -1 out front, and then we can change all those square roots of -1 to I. So really, you could just pull an I out. That's how I say it. When you have a square or a negative under the radical, just put an I out in front of the radical and get rid of the negative under the radical, and you're going to be good. So let's look at 7a here. Square root of -1 is I, and the square root of 16 is 4. So we would write this as 4i. On part B, this is a minus I times 9, and we would write that as -9i. So just like with, like if we had a 9x, we wouldn't put x9. We normally put the numbers first. Same thing with these. On letter C, all I can do is change the square root of -1 to I. We like to put the I in front of the radical, because if we put it behind the radical, sometimes it gets confusing. It looks like the I is under the radical. The I will never be under the radical. And on letter D, notice I can write 27 as the square root of 9 times the square root of 3. So square root of 27 is not a simplified radical. So this becomes 3i times the square root of 3. All right, let's move on. On number 8, it says what kind of radicals can be combined? That would be using addition or subtraction, and we would say like radicals. Like radicals have the same root and the same radicand. So they're not both just square roots. They have to have the same number under the radical. So you can see on number 9a, those are like radicals because they both have a square root of 7. They're both square roots, and the radicand is 7 in both. And I want to make another comment here. We combine like radicals just as we do like terms. Very similar. So for example, if I had 2x plus 3x, I would add my 2 and 3, and I'd get 5x. So when I'm adding 2 square roots of 7 and 3 square roots of 7, we're going to add the 2 and the 3, and we have 5 square roots of 7. Notice in part B, these are not like radicals because they don't have the same radicand, and so this is already simplified. On letter C, we have our square root 2 radicals. Those are my like radicals. Notice the second one here, this is a -1. So we're going to, 7 and -1 gives us 6 square roots of 2, and then we'll just write the other one separately. On letter D, notice the first number 2 is not even a radical. So certainly 8 square root of 3 can't be combined with the 2. They're not like radicals. 2 is not even a radical. So this one's already simplified. All right, I just want to mention what we call complex numbers, because that's what we're dealing with here with these i's. A complex number is any number that can be written in the form a plus bi, where a and b are real numbers. So let me show you what that means. If you had 3, that's actually considered a real number, but it's also considered a complex number based on this definition. We could write 3 as 3 plus 0i, so notice a is 3 and b is 0. So in this case you don't have an imaginary part, it's just got a real part, and so the number 3 can be written this way to show you that it can be written in the form of a complex number. It is considered a complex number. Same thing with 5i, that would be considered 0 plus 5a. So here a would be 0 and b would be 5. If you had something like 4 minus 2i, of course a is 4 and b is negative 2. So basically all of our real numbers are included in the complex numbers. That's when b is 0. And all the numbers that have an I in them are considered imaginary. So basically, the complex numbers are made up of the real numbers and also the imaginary numbers. We're putting them all together, and so now we have a bigger set of numbers called the complex numbers, which are the numbers we'll be working with. All right, so on number 10, we're going to have to simplify expressions like this when we work with the quadratic formula and when we solve quadratic equations. So let's go ahead and practice this. So if you look at letter A here, the square root of 24, first of all, that's not simplified. We could write it as the square root of 4 times the square root of 6, and square root of 4 is 2. So I'm just going to rewrite this and put the square root of 24 in its simplified form, and we're done. Now if you look at letter B, look at the radical. Square root of negative 28, first of all, it's imaginary, but also 4 is a factor. And so let's go ahead and take care of simplifying the square root of negative 28. This is going to be I times the square root of 4 times the square root of 7, or 2i square roots of 7. And I'm going to go ahead and plug that in place of the square root of negative 28. And now to simplify this expression, we're going to break the fraction into 2. So 12 over 32 minus 2i square root of 7 over 32. And we can simplify these fractions. 12 over 32 we can divide by 4. In the numerator and denominator we get 3/8. And 2 over 32 we can divide by 2, and we get 1/16. So we end up with 3/8 minus I square root of 7 over 16. You could put a 1i there, but you don't really need to put the 1. All right, so you might try letter C if you want to see if you can do that. And then you can check my solution. All right, we're going to go ahead and do it now. I hope that you realize you can always stop the video anytime and try problems if you think you understand, and then you can always watch the solutions. All right, so let's see. We need to first simplify the square root of negative 18. So that's going to be I times the square root of 9 times the square root of 2, or 3i square root of 2. So let's replace that in our expression, break this into 2 fractions, and then simplify our fractions. So in the first one we can divide by 3, we get negative 5/11. And in the second one we can also divide by 3, we get 1 over 11. So our final answer is negative 5 over 11 plus I square root of 2 over 11. And that's all for this video.